Building bridges, especially across water, has been one of man's most enduring challenges. Of all the different forms of bridge design, the most famous is the suspension bridge.
In this program, we admire the slender elegance of the Swiss Bay Bridge in the Czech Republic, stand in awe of the vast new Storebelt Bridge in Denmark, but we start in England with the finest work of one of the fathers of modern engineering. This is the Clifton Suspension Bridge near Bristol, a 19th century engineering masterpiece. 214 meters long, it was the challenge of a lifetime for one of Britain's greatest engineers, Isambard Kingdom Brunel. He described it fondly as "my darling, my first child," even though there were many difficulties in the history of its construction.
In 1829, the city fathers of Bristol announced a competition to design a suspension bridge crossing the Avon Gorge. They'd been considering a bridge for many years, but it was only with the development of wrought iron that an affordable crossing could be built.
After much deliberation, the contract was awarded to the 24-year-old Brunel. Although young, he had already notched up several years' experience working for his father, himself a renowned engineer. But this was his first bridge.
This is how a suspension bridge works. Two towers, one at either end, support a heavy cable or chain across the middle. This is the most important part of the bridge. It's really heavy, and as its weight pulls it down, it tries to drag the towers inwards. So it has to be anchored at both ends. Hangers are attached to the cable along the length of the bridge, and the deck is assembled last. It's a really simple concept, and it can be used to span huge distances, but it's the anchors which are critical to holding the bridge in position. This is the top of the anchor point, where the chains meet the ground and are anchored back into the rock 20 meters away down there. Beyond here, the chains are splayed out like a fan, so that when they're pulled back towards the bridge, they lock solid. There are 3 chains on each side of the bridge. Each link is 8 meters long, and it's made up of between 10 and 12 flat metal plates, like this. They're like giant spanners, bolted together at each end. They built the chains in situ, starting 1 plate thick and then adding the parallel links in succession. They're the heaviest part of the bridge. Between the piers, the chains weigh 550 tons.
The vast weight of the chains is supported on the 2 huge piers, and at the point where the chains and piers meet are the saddles.
This is the saddle room at the top of one of the piers, and these saddles carry the huge forces from the chains, pulling downwards into the stone pier beneath us. The saddle itself sits on roller bearings, so it can move backwards and forwards just a little bit as the chains expand and contract.
At each joint of the chains are the vertical suspension rods, which take the weight of the deck. You can see that each rod is joined to a different chain, either the top, the middle, or the bottom one, sharing the load of the deck between them.
This is one of the cradles under the bridge used for maintenance, and you can really get an idea of the size of the gorge they were trying to cross. Above me is the heavy wooden deck of the bridge, supported on these lattice girders. There's very little other bracing. A suspension bridge is exactly what it says. It's suspended, and you can really feel it move up and down as the traffic comes on above. Many events conspired to delay construction. Brunel oversaw the erection of the two piers at either end, but in 1843, work stopped due to financial difficulties. By the time they restarted, Brunel had died.
During the decades of inactivity on the bridge, Brunel would go on to many other remarkable engineering achievements, but he never lived to see his favourite bridge finished.
When the bridge was complete, it was decided to do a load test to measure its deflection. 500 tons of stone was spread over the roadway, and it sagged just 7 inches, 175 millimeters. It was 1864, and the bridge, which had taken 33 years to complete and outlived its designer, was ready for opening.
The challenges overcome in the construction of the Clifton suspension bridge are summed up in this Latin inscription. It means, "A suspended way made with difficulty." The bridge is in as good a condition now as it was when it was first opened, and is still in regular use. It stands as a testament to the achievements of the Victorian engineers, and in particular to the brilliance of Isambard Kingdom Brunel. Although the principle of the suspension bridge has remained unchanged, advances in modern materials and techniques have enabled us to build bridges with spans that dwarf their predecessors. This is the Storebælt suspension bridge in Denmark, one part of the Storebælt crossing that links Copenhagen to the mainland. The construction of the crossing was one of the world's largest engineering projects of the 1990s.
The entire crossing is 17 kilometers long. There's 3 main elements: a tunnel, the West Bridge, and what we've come to look at, the East Bridge. With its total length of 6.8 kilometers, it's the longest suspension bridge in Europe.
Hi.
Hi. 16,000 cars are expected to cross this bridge every day. It'll pay off the cost of construction by 2012.
The bridge has a main span of 1,624 meters, with 2 side spans of 535 meters and 23 approach spans totaling 4,000 meters. It took 7 years to build.
It works on exactly the same principle as the Clifton suspension bridge. The deck hangs from the great cables which run over the piers, and the cables are anchored at each end to huge concrete blocks like this one here.
The towering piers are made from reinforced concrete, and their main function is to support the cables at the top. They were cast in molds, which moved up in stages as the concrete cured.
The piers are among the tallest of any bridge in the world. At 254 meters high, they exceed the height of the Golden Gate Bridge by 26 meters. The A-shaped design of the piers is really very simple. 2 large crossbeams connect the legs together, but the only restraint the legs provide to the deck is to prevent it moving from side to side.
Fortunately, there are lifts inside the piers to get up to the top.
This is one of the giant saddles. There are 2 at the top of each pier, over which the cables run down towards the deck below. A bridge on this scale is only possible because of the extraordinary advances in materials and construction technology in recent years. These, the cables, are the essential element of any modern suspension bridge. Inside this protective casing are 18,648 wires, each 5 millimeters in diameter, made of ultra-high strength steel.
The cables supporting the deck are 3 kilometers long, and the strength of the steel is such that each individual wire could carry the weight of 3 large cars before it would break.
To get the cables up in position, they first laid a thin pilot wire across the seabed and winched it right up here. And then they pulled the top of the piers back, bending them like a ruler over a meter to compensate for the weight of the cable, which would tend to pull the tops of the piers back inwards again.
The main cables were constructed using a process known as cable spinning, where 4 of the wires were laid out at a time. Cable spinning went on 24 hours a day and involved more than 9,000 journeys up and down the bridge. The cables were completed in just 4 months, a remarkable achievement. Once the cables were completed, the deck could be assembled. The box sections that make up the deck were lifted up from barges using 2 cranes supported on the main cables. There were 56 standard sections, prefabricated in Italy and brought to Denmark on ships. Each of them was 48 meters long and weighed 550 tons.
I'm right underneath the roadway, inside the bridge, and it's like a gigantic hollow box section, 31 meters wide and 4 meters deep. And this is where the bridge gets its stiffness, solving the problem faced by the early bridge designers 100 years ago. These trusses run right across the bridge, and they give it the twisting or torsional stiffness it needs. They act like walls. Like this empty matchbox, it's easy to twist without the drawer inside, but when I put the drawer back in, then it has a lot of twisting or torsional stiffness. And that's because the walls at each end hold the outer skin in place, and that's really where the box gets its stiffness from. At each end of the bridge deck, you can see the huge hydraulic buffers that allow slow movement of the bridge to take place, like expansions due to temperature change. But they'll lock solid if there's any shock loading on the bridge, like all the cars braking suddenly on the deck above. It's a bit like the way a seatbelt works. You can lean forward slowly, but if there's a sudden shock, it jams. Usually when you drive over a bridge, you can hear the clickety-click of the car going over the expansion joints every so often. These are the little gaps that allow the bridge to swell or contract with changes in temperature. On this bridge, there are no expansion joints in the whole 2.7 kilometers of the steel deck, and it's all taken here at each end with one gigantic expansion joint that can move up to 1 meter in both directions. It works a bit like a concertina, and each of the little joints stretches a little bit to give it the movement it needs altogether.
The anchor blocks for the bridge were designed to minimize their appearance using triangular concrete elements to anchor the cables. They are wedge-shaped, and each one weighs 325,000 tons.
I'm inside one of the splay chambers, right at the bottom of the huge anchor block at each end of the bridge. It's like being at the bottom of some giant pyramid.
The splay chamber is where the wires splay out in bunches from the cables and are locked into the huge concrete anchor blocks, transferring all the force from the weight of the bridge into the foundation below.
These are the individual wires holding up the bridge, and you can see how they're looped around the cable shoe at the bottom, and the cable shoe is bolted into the concrete foundation. In fact, these wires are welded together so they're continuous and they're looped round and around the bridge. If we were to lay out all the wire on the bridge, end to end, it would go around the world 3 times. Underneath the splay chamber, these are the other ends of the bolts holding the wires and the cable shoes in place. This is where the force has finally been transferred into the huge concrete anchor block. It's the end of the line. See? No more force. Bridges on this scale are not simply about getting from A to B. They're part of a much larger framework. In the case of Storebelt, uniting 2 halves of a nation. But this bridge is also an international achievement, bringing together engineering expertise from many countries to provide the best technical solutions. So where does the suspension bridge go from here? Perhaps we need to take a fresh look at the whole concept.
Bridges are a highly visible form of engineering design, and it's important that they blend into their environment in a sensitive and attractive way. In a rural setting, the suspension bridge has a clear advantage. Its shape smoothly reflects the forces inside it, like many plants and trees. This is Lake Vranov in the Czech Republic, a popular holiday resort. Tourism is an important industry here, and the local officials decided to replace the old ferry service with a permanent crossing to make it easier to cross the lake. The result was this beautiful and extremely slender suspension bridge across an inlet of the lake called Swiss Bay. It's a pedestrian bridge, completed in 1993, and it links the restaurants of the small town of Vranov to the beach on the other side of the lake.
The Swiss Bay Bridge stretches the concept of the suspension bridge by finding new ways to stiffen the deck without compromising its shape or proportions. Like the other suspension bridges we've seen, the deck hangs from the cables and the cables are anchored at each end. What's special about this bridge is it's very thin, quite unlike the chunky deck of the gigantic Storebelt. As you can see, this deck is less than ½ a metre thick. The deck's made of concrete sections, each 3 meters long, precast and assembled here on site, suspended from these hangers. But as suspension bridges get more slender, they get more susceptible to wind-induced vibration, just like the early suspension bridges last century, and the spectacular collapse of the Tacoma Narrows Bridge in 1940. In the wind, a thin bridge deck can bounce up and down. Waves can form in the deck, a bit like this rope, which are very uncomfortable for people on the bridge, and in the extreme can bring the bridge down.
This suspension bridge is different. The deck on this bridge is being pulled down by cables running through it, as well as being pulled up by the cables from which it hangs. This system of pre-stressing the bridge gives it the stiffness it needs. Other cables inside compress the deck along its length. It's these internal cables that allow the bridge to be so slender.
Concrete is very strong in compression, but it cracks easily in tension. Under normal circumstances, the flexible deck of a suspension bridge would quickly crack a simple concrete slab, leading to corrosion and possibly worse. But if the concrete is already in compression, using wires that run through it specially for the purpose, then when the deck bends, it won't crack, giving it much more strength and rigidity. Imagine that these chocolate biscuits are pieces of the bridge deck hanging on the hangers. Assembled in a line side by side, they're quite loose and you can move them around easily. But if we stretch a rubber band around them, then they get compressed together and it makes a stiff beam. That's exactly how the bridge deck works. Once the concrete sections were hanging in position, the wires were threaded through the deck. Hydraulic jacks then pushed the concrete sections tightly together into their arch shape. 4 of the wires in the deck were then tightened and locked off, leaving the deck in compression. The gap where the jacks had been was filled with concrete. Once that had set, the last 2 wires were tightened, pulling the whole deck down onto the abutments firmly.
The main stiffness of the bridge comes from the pre-stressing, but there are other tricks too. The deck narrows as it reaches the middle and flares out at each end. This helps dramatically to increase its lateral stiffness when blown by the wind.
The bridge gets even more stiffness by using inclined hangers and an inverted V-shaped pylon at each end. The triangular shape made by the pylon, the hangers and the deck make it very difficult for the deck to sway from side to side or to twist. The old rule of marching soldiers having to break step when they crossed a suspension bridge for fear of destabilizing it was for good reason. But computer simulations and wind tunnel models of this bridge showed that the system of cables up above and in the deck prevent it from moving almost completely, even if it does start to vibrate. So it can't possibly shake itself to bits. Like the Clifton suspension bridge and store belt, this bridge at Swiss Bay is exploiting one of the oldest of all bridge concepts. The same principle as a simple rope bridge in the jungle. For me, the suspension bridge is the most attractive of all bridge forms. Like a hammock on a sunny afternoon, it blends perfectly with its surroundings.
In our next programme, we travel to Italy to discover the origins of concrete at the beautifully preserved Pozzuoli Amphitheatre near Naples, and then to France, to the striking Plougastel Bridge near Brest. And we stay in France to explore the remarkable design of the new TGV station in Lyon.